Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So you can recall that in the last lecture we have learned various properties of the treatment and block totals. And since our aim is more towards the testing of hypothesis for the treatment effect, so we know that when we are trying to do so, then we need the adjusted treatment totals and unadjusted block totals. So that is why our most of the results are oriented on adjusted treatment total and unadjusted block totals, but it does not mean that we cannot consider the result for the adjusted block totals and unadjusted treatment totals. In fact, in the last lecture towards the end I had shown you the same result that we had proved for the equation q is equal to c tau, I have proved it for the p is equal to d beta also. So now in this lecture we are going to move further and we are going to consider some more properties of incomplete block design which are related to the treatment and block totals. And these properties will help us understanding the different types of things which are happening inside the incomplete block design analysis of variance. Right. So, let me try to take these properties one by one and I will try to explain you that what are the interpretation and what are the intricacies that they are going to solve. So, now the first property which I try to take here is about the ranks of the matrix C and D with their connection to the number of blocks and number of treatment. So, we have here the first lemma which is B plus rank of C is equal to V plus rank of D, and you will see that how this result is going to help us in understanding a very important result. So, first we try to have the proof of this result which is very simple. So, we try to consider here a B plus V cross B plus V matrix like as here whose elements are here matrix K, incidence matrix N, N transpose N, R matrix, and this matrix is indicated by here A. And if you try to see how this matrix is coming, do you remember this equation that was the set of normal equation that you had obtained in the format of vectors and matrices, and if you try to see here this part. So, we have considered this part which is the sum matrix of the coefficient matrix of this normal equation. So, at least you should know that from where we are trying to consider, yes, we have a certain objective which we want to prove, and that is why we are trying to consider this sum matrix. Now, we try to use here a result from the matrix theory that the rank of a matrix does not change by the pre-multiplication of the non-singular matrix, right. And so, we try to consider here two different non-singular matrices here M and say here S. So, M here is given by here you can see here this is an identity matrix of order B and identity matrix of order V, and then we have here two matrices here and here in M and S respectively, and the other matrix here is null matrix. Now, you can ask me why I am trying to choose this structure for the non-singular matrix. Well, this will get very clear as soon as I come to the next step, right. So, now using this result we can say now because M and S are non-singular matrices. So, we can write down here that rank of A is equal to rank of M A is equal to rank of A S. So, now let us try to find out the matrices M A and A S. So, M A can be obtained here, just try to write down this matrix here M, then here A, just try to multiply it, it will come out to be like this K N null matrix 0 and C. and similarly if you try to find out here AS, you can simply write down here S, then multiply by A, and you will get here here D and null matrix, and then here R. Now you have here these two matrices, this one and this one. So rank of both the matrices, they are going to be the same. So you can write down here rank of this matrix K and null matrix C, and rank of D and null matrix and R. So I can write down here as a rank of K plus rank of C, and then here on the right hand side of the equality sign, this will become here rank of D plus rank of R. Right. Now if you try to see here, what is here rank of K? K was a diagonal matrix K1, K2, Kb, and R was the diagonal matrix here R1, R2, Rv, like this. Right. So the rank of K matrix is going to be here B, and rank of D matrix will remain as here, and rank of this R is going to be here V, and rank of C comes over here. So now you can see here that that is what we have proved, B plus rank C is equal to V plus rank of D. But now what are you going to get after this result? And one thing you can see here, that when you are trying to multiply here this and this matrix, here you are getting the matrix here C, and that is why this matrix M and S were chosen. For example, M was chosen here like this, which can give us here a matrix C, and this S matrix was chosen in a particular way such that its multiplication with A will give us here D. So that is a mathematical trick that we have followed. Now what is the advantage of this thing, that is now we have to see. Now if you try to remember, when we discussed the C matrix, then we had proved that the row sums and column sums, they are 0, and similarly if you try to consider the matrix D from P is equal to D beta, and C was obtained from Q is equal to 3 tau. So for D matrix also one can prove that the row and column sums, they are 0. So for D matrix also D into EB1 will be equal to 0, that is null vector. So now you can see here that the both C and D, they are rank deficient matrix. And what will be the exact rank, that we cannot say at this moment, but surely there is one constraint which is ensuring that the rank of C is going to be smaller at least by 1. So we can write down here that rank of C is less than or equal to V minus 1. And similarly, when you are trying to consider the matrix D, so D is a B cross B matrix, but we know that there is at least here one constraint. So whatsoever be the rank of D, at least that is assured that it is not going to be a full rank, that is B. And it is also assured that because of this one constraint, the rank is going to be deficient at least by 1. So we can write down in general here as a rank of D is less than or equal to B minus 1. Right. So that is a very important result that we will see. But now in case if I try to take a particular value of here this rank of C, then let us try to see what happens, and for that we have one result here in the form of this lemma, that if rank of C is equal to V minus 1, then all block and treatment contrasts are estimable. Right. Let me first try to prove this result, and then I will try to show you the magic of this lemma, and that will clarify many things what you have learned in the earlier lecture in the incomplete block design analysis of variance. Right. So obviously now if you see here, if rank of C is equal to V minus 1, so it is obvious that that all the treatment contrasts are estimable. Right, because do you remember that when we had learned the one-way and two-way analysis of variance, then we had the problem that when we introduced the general mean effect term in the model, at that stage all the parameters were not estimable, but when we had not introduced the general mean effect in the model, before that there was no problem of estimability of the parameters, and we had considered, or we had actually found that all the parameters in the model with the general mean effects, they are going to be estimable when the parameters can be expressed in the form of contrast, right. So, what we had done, we had made the rank of the corresponding matrix to be deficient by 1. So, that is what we are trying to say here, that in this case also, if the rank of the C matrix becomes deficient by 1, that means in order to satisfy this thing, the treatments have to be expressed in the form of contrast, and then they are going to be estimable. Now, we have just proved the result that B plus rank of C is equal to V plus rank of D. So, in case if I try to substitute here rank of C equal to V minus 1 here, then let us see what do we get. So, then rank of D becomes here, say rank of D plus V is equal to rank of C, which is here V minus 1 plus here B, and so here this V we get cancel out, and we get here rank of D is equal to B minus 1. So, now if you try to see what are you going to do, you are trying to say rank of D becomes equal to B minus 1, and because of the same reason which you have given here, that when rank of C is equal to V minus 1, then all the treatment contrasts are estimable. Similarly, we can see here that when rank of D is equal to B minus 1, then all the block contrasts are also estimable, right. And if you try to recall that when you consider the randomized block design, I will try to show you after we complete these properties, that I will try to employ these results in the setup of a randomized block design, and then I will try to show you that in the case of randomized block design, if you try to find out this matrix C and D, then their ranks will come out to be as V minus 1 and B minus 1 respectively, and that is why we had considered the null hypothesis in terms of the elementary contrast of the parameters. And once rank of C becomes V minus 1, then so C is related to the adjusted treatment total. So then obviously the rank of D also becomes B minus 1, which is related to the adjusted block totals. So that is why if the elementary contrast about the treatment effects, they are estimable, then the elementary contrast about block effect, they also become estimable. And that is why we did not had the problem of estimability in the case of randomized block design, and we did not had to bother about the concepts of say adjusted versus unadjusted sum of squares. But in general, in the case of incomplete block design, this is not happening. So, we have to introduce and understand these concepts, right. So, now this gives us an idea that what are the conditions under which Q and P, they are going to be orthogonal. Q and P, if you try to recall, the Q is the adjusted treatment totals, and P here is the adjusted block totals. And you will see that in case if Q and P becomes orthogonal, then we have the same situation that we discussed in the case of randomized block design, because they are going to be the adjusted treatment totals and adjusted block totals. So, in this case, if Q and P are orthogonal, then the TSS can be partitioned into say the SS block plus SS treatment plus SS error, and where both are going to be adjusted. But this was not happening when we were trying to consider the general structure of incomplete block design, right. So, first let us try to find out what are the conditions under which both these adjusted totals, that is for treatment as for block, they are going to be orthogonal, and this definition will give rise to so called orthogonal designs. So, now if you try to see, we have defined the here Q and here P by these two expressions. Q is equal to V minus N transpose K inverse B, and P is equal to P minus N R inverse V. Now, basically you have to find out here the covariance between Q and P. Now, you can use any of the approach that we have discussed earlier in the last lecture, right. You can use summation approach, you can use matrix approach directly, or you can convert the variables in terms of D1 and D2, all are going to give you the same result. Just for the sake of illustration, I have chosen here the third approach that we considered in the last lecture, which is based on D1 and D2. So, I can write down here Q here as say like this, P here as say like this, right. Now, here you have to use the same relationship with that we used in the last lecture. I am not going to repeat it, but then you have all the slides, you can look from there and can find out these expressions. So, now the covariance between Q and P, that is going to be this matrix into the second matrix transpose into the covariance between y and y. So, covariance between y and y is the variance between y, which is sigma square I, which is here. Now, after this you simply have to simplify these two matrices, you simply have to multiply them, and you have to use the relationships that we have illustrated in the last lecture. So, you can see here that D1 D2 prime is here like as a N transpose, D1 D2 transpose R inverse D1 K2 transpose, that will come here like this, and then similarly you try to substitute here all the corresponding expressions, and finally you will get here N transpose K inverse N R inverse N transpose minus N transpose into sigma square. Now, this is the covariance between Q and P, right, and can you really say that it is going to be 0 or a null matrix or null vector? You cannot say anything in general, right, unless and until some specific cases happen. So, now you can see here that this Q and P means, or equivalently the Qi and Pj, they are orthogonal when covariance between Q and P is equal to null matrix. So, now if you try to see, you have obtained here this expression. So, if this expression becomes a null matrix, then it is orthogonal, that means Q and P are orthogonal. So, let me try to write down here this condition. Now, you see, if you try to recall, you had this definition of C where you are getting here this term N transpose K inverse N, and if you try to see here in this definition also you are getting here N transpose K inverse N. So, now if you try to replace this quantity by here R minus C and then try to simplify it, we get here this condition C into R inverse N transpose is equal to null matrix, right. And alternative, we can solve this equation like this. Suppose we try to consider here this term once again here, and if you try to see here, you have here a term here like this one N R inverse N transpose, and if you try to recall the definition for this here D was K minus N R inverse N transpose, and here also you have this term here N R inverse N transpose here. So, we try to substitute here in this term the term here like as K minus D, and we simply try to simplify it, then we get here one more condition, equivalent condition, which is N transpose K inverse D is equal to null matrix. So, now we have here three conditions. This is here the first condition that we have written, this is here the second condition, and this is here the third condition. So, I can write down here very easily that Qi and Pj, they are orthogonal if N R inverse N transpose K inverse N is equal to N transpose, or equivalently N R inverse C is equal to null matrix, or equivalently D K inverse N is also equal to null matrix. So, if any of these three conditions are satisfied, then we have the specification of an orthogonal block design, right. So, a block design is said to be orthogonal if Qi's and Pj's are orthogonal for all I and j. Right. So, the condition for the orthogonality of a block design is that either of these three conditions, this that you have just found hold true. And you can verify, although we will try to discuss it, that in the case of randomized block design, the design comes out to be an orthogonal block design. And that is why there is no discrimination between the concepts of adjusted and unadjusted blocks or say treatments sum of squares, because they are orthogonal. So, either you try to take adjusted or say unadjusted, they are going to be the same thing. Right. Now, we try to just consider some properties of this orthogonal block design, because that is going to play a very important role in understanding a couple of concepts. So, the first lemma says that if n I j upon R j is constant for all j, then n I j upon k I is constant for all I and vice versa. And in this case, n I j will come out to be here k I R j divided by n. Right. So, this condition is going to help us a lot, but before we try to see the proof. So, well, if I try to see here, if n I j upon R j is constant for all j, then means I can write down here n I j upon k I is equal to say q I, right. So, this means here n I j is equal to a I into R j, where a I is some constant, right. And then if I try to take the summation over j on both the sides, you can see here this will come out to be here say a I and then summation over R j, which is equal to here small n, that we know. So, now you can see here that this k I becomes here a I into n, or a I is equal to k I upon n. So, now I can substitute here this a I here, and then I can write here that n I j upon R j is equal to k I upon n, or I can write down here n I j is equal to k I into R j divided by here n, or say n I j upon k I is equal to R I upon. So, this n I j upon k j will become here R j upon n, and you can see here this is independent of I, or hence this lemma is proved. Well, how this lemma is going to be useful, that we will try to see. But before that, just try to recall the definition of the contrast. Although we have discussed it in the beginning of the course, but just for the quick revision, I have given here this definition, that a linear function summation over j goes from 1 to v c j tau j, that can be expressed at say c transpose tau, where this c1, c2, cv, they are some given constant, given numbers, such that summation over j cj is equal to 0. This is called the contrast of tau j's. And contrast this summation over j cj tj tau j, which is expressed at c prime tau with c is equal to some this vector of c1, c2, cv. In treatment effects, tau 1, tau 2, tau v is called an elementary contrast if c has only two non-zero components 1 and minus 1. Right. So, the elementary contrast in the treatment effect, they are of the form like tau I minus tau j. So, if one can write down here say 1 minus 1 and say here tau I tau j, right. And then means if you have more than two treatments, then this will become here 0, 0, 0 and then 1 and then minus 1 at some I and jth positions here and tau j, and all other values will be here 0, and then we will get here the elementary contrast tau I tau j. So, now how this elementary contrast is going to help us, that we have to understand, and you try to recall that how this definition of elementary contrast had helped you in the case of two-way analysis of variance. Now, we want the design of experiment, or we want to design an experiment where all the elementary contrasts are estimable. Right. So, now based on this wish, we have a definition of connected design, and this says that a design where all the elementary contrasts are estimable is called a connected design, and if not, otherwise it is called as disconnected design. Now, the question comes here, you understand the physical meaning of this word connected, right? That means things are joined, but what is the physical meaning of this concept? In case if you can understand that thing, then the understanding of incomplete block design and its relation with this definition becomes simpler. So, let me try to show you here the physical meaning of this connectedness, and then I will try to show you a graphical display also. So, if you have any say two treatment effects, say tau I1 and tau I2, then if it is possible to have a chain of treatments, you can see here that here I have tau I1 and here I have here tau I2, and in between I have the treatment here tau 1j, tau 2j up to here tau and j, and this chain of treatment is such that two adjoining treatments in this chain occur in the same block. That means this tau I1 and tau 1j they occur in same block, tau 1j and tau 2j they occur in the same block. So, do you remember that when you are trying to conduct the experiment, you are always trying to give the treatments to different blocks, and you are trying to say here that the two adjoining treatment they are in the same block, right. So, in this this type of design, that is the connected design, within every block all the treatment contrasts are estimable, and pairwise comparison of estimators have similar variances. Now, we are going into deeper and deeper, and then we will try to come back, and then you will try to see how the things are interrelated, and they are trying to help us different intricacies of this incomplete block design. So, now just for the sake of an illustration for this connected design, we try to consider an example. So, we are considering here a disconnected incomplete block design such that we have we have here 8 blocks. So, B is equal to 8 and the block numbers are given by here first, second up to here 8th, and number of plots in every block is 3, that is k equal to 3, and V, that is the total number of treatments here, they are here 8. So, now we have here block number 1 which has the treatments 1, 3, 5, block number 2 which has the treatment 2, 4, 6, block number 3 which has the treatment 3, 5, 7 and so on. Now, in case if you try to represent these blocks graphically, so one possible way is that I can indicate here by such a diagram. So, you can see here this is 1 and here 3, 5, 7, 2, 4, 6, 8, they are trying to represent the different treatments. Now, if you try to see what is happening between this and this, there is no connection. This means here what? Suppose you want to go from treatment number 1 to treatment number 5. So, you have here first option that you go from 1 to 3 and 3 to 5. So, I can write down here tau 1 and tau 3 and then or here tau 5 first, and then I try to write down here tau 3 in between. So, you can see here that the elementary contrast of tau 1 tau 3 and tau 3 tau 5 they are in the same block. And similarly, if you go from here treatment number 1 to treatment number here 7. So, first option is this, you can go from directly from 1 to 7, or second option is this, you can go from here 1 to 3, 3 to 5 and 5 to 7, or third option is that you try to go from here 1 to 5 and then 5 to 7. So, in this case what you can see here, I can write down here tau 1 and tau 7, and then in between I can write down here tau 3 and tau 5, or I can write down here tau 1 and tau 7, and then I try to write down here tau 5. But if you try to move from treatment number 2 to treatment number 7 or vice versa, you can see here there is here a break. There is no connection between the two. So, we cannot reach to treatment 7 from say treatment number 2 or 4 or 6 or 8. And similarly, we cannot reach from any of the treatment from this part to this part. So, from this point of view, the design is disconnected. Now, I try to create here an example where the design is connected. So, you can see here we have here the treatment number here 1, 2, 3, 4, 5, 6, 7, 8. Now, if you try to see, if you want to reach from any treatment to any treatment, you can always reach. For example, if you want to reach from treatment number 1 to 3, first option is this, you can go from here directly, or you can go from here 1 to 2 and then here 2 to 3. So, you can see here tau 1 and tau 3, and then I can write down here tau 2 in between. So, this tau 1 and tau 2 they are forming an elementary contrast, tau 2 and tau 3 they are forming another elementary contrast, and they are in the same block. And similarly, if you try to go from any treatment to any treatment, for example, if you want to go from here 7 to 3, you can see here you can go from 7 to 1 and 1 to 3, or the other alternative route is that you can go from 7 to 4 and 4 to here 3, or the other alternative route is that you can go from 7 to 6 and then from 6 to 3. So, in this sense, if you try to see in this structure, you can go from one treatment to other treatment without any problem. So, from this point of view, this design is said to be connected design. So, now I hope that this concept is clear, because once you see it graphically, then it becomes more clear here, and this is what I have shown you here, that if you want to go from here, for example, treatment 6 to here treatment 2, you can see here you can go from a treatment number 5 and then 5 to 4 and then 4 to 3 and then here 3 to 2 and then here 3 to 1, or the other alternative is that you can go from 6 to 3 and then 3 to 2, or you can go from here 6 to 7, 7 to 8, 8 to 1, 1 to 2, or 6 to 7, or from 7 to 2. So, I can say here that a design is connected if every treatment can be reached from every treatment via lines in this connectivity graph. This is the graph which I have shown you here, right. So, now we have a very important result here, and this theorem says that an incomplete block designed with V treatment is connected if and only if rank of C is equal to V minus 1. Now, if you try to see what are you really trying to do, you are assuming here that the design here is incomplete block design, and suppose if rank of C is equal to V minus 1, then you are trying to say that the design is connected. That means all the elementary contrast of the treatment effects in this case, they are going to be estimable. And once you try to assume that rank of C is equal to V minus 1, then you already have proved the result that rank of D is going to be here B minus 1. So, in case if rank of C is equal to V minus 1, then all the elementary contrasts of the treatment effect, they are going to be estimable, and in turn when rank of C is equal to V minus 1, then the rank of D is going to be B minus 1, and all the block effects, they are in the form of elementary contrast, will become estimable. And if you try to recall what was happening in the case of randomized block design, you had expressed the null hypothesis for the treatment and block effect in the form of an elementary contrast. So, now if you try to see, when you are trying to express those treatment combinations and related to the treatment effect or to the block effects, if you are trying to express them in the form of an elementary contrast, they are going to be estimable, and if one of them is estimable, then other one also becomes estimable if the design is connected. And since you are assuming that rank of C is equal to E minus 1, so this is a necessary and sufficient condition. So, this condition of connectedness becomes true. So, now you can see this interrelationship between rank of C, rank of D, estimability of parameters and elementary contrast. Right. So, now that is the time where you have to just think once again and try to see what are you trying to do. Right. Now, we try to see here the interrelationship between the connectedness of block design and the orthogonality of this adjusted treatment totals and adjusted block totals. Right. So, when we have a connected block design, that means all the elementary contrasts, they are going to be estimable. Then in that case, the adjusted treatment and adjusted block total, they are going to be orthogonal. If this condition holds true, that is, the incidence matrix is expressible in the form of R k transpose upon n. So, now let us try to have the proof of this result, and after that you see, I mean, everything will become very clear to you. So, now in case if I try to see here that this is a necessary and sufficient condition. So, first I try to consider here the if parts, that we assume that n transpose is equal to R k transpose upon n, and if you try to recall, you have just found the expression for the covariance between Q and P. So, we try to bring this sigma square here on the left hand side, and the expression here is like this, and you simply try to substitute here n transpose equal to R k transpose upon n in this expression. So, you get here like this, you can substitute here, I have substituted here, and now if you try to simplify it. So, you can see here this term here k transpose capital K inverse k, this can be simplified here, just use the simple matrix multiplication. You can see here this is coming out to be here simply here n, no issues. And this term here R transpose capital R inverse, if you try to substitute these values and try to multiply it here, you are going to get here E 1 V. So, now if you try to see here these terms are given here, you can see here this is here K inverse and then another K transpose K inverse K, and then here this is the term here R transpose capital R inverse. So, if you try to substitute here all these values, you get here like this, and if you simply try to just solve it here, this n gets here cancel out, and if you try to see here, this quantity simply becomes here R k transpose upon n minus n transpose, and this is here n transpose because you have assumed it. So, this becomes here null matrix. So, covariance between Q and P becomes a null matrix when this condition holds true. This is the given condition. Now, in case if you try to take the only if part, that is also straightforward using the concept of linear estimations. So, I can write down here that covariance between QP is equal to say null matrix. If this condition hold true, that is the same condition that you had obtained earlier for the orthogonality, and if you try to remember, we had substituted here the value of n transpose K inverse n using the definition of here C, and this condition came out to be here C R inverse n transpose equal to null matrix. So, now we try to assume here, suppose this part here R transpose n transpose let it be equal to A, some matrix whose column vectors as A1, A2, AB, right. So, they are the columns of matrix A. Now, since the design is connected, so the columns of A are proportional to AV1, and also the row on the column sum of this matrix C are 0. So, I can write down here that CE1, EV1 and say CE1 is equal to null vector and CA is equal to null matrix. So, if you try to see here, I can write down with this here say C times here this column vectors of A is equal to here null matrix, or I can write down here that this AI is simply proportional to EV1, right, where this AI is equal to some alpha I EV1, where alpha i's are some scalars constants. So, this gives us that A is equal to R inverse N transpose, which is equal to here EV1 alpha transpose, where alpha is some vector of alpha 1, alpha 2, alpha b. And now, if you try to see here about this N transpose, this is equal to here R EV1 alpha. Now, if you try to simplify here R into EV1, you will get here this column vector of R1, R2, RV. So, I can write down here simply here say R alpha prime, right. And if you try to multiply pre-multiply on both the side of this term by E1V. So, I can write down here E1V N transpose is equal to K1 K2 KB transpose, which is equal to here E1V R alpha transpose, which is equal to here simply here N alpha transpose. So, I can say here that this is actually here K, that is the column vector of K1 K2 KB. So, this K is equal to N into alpha transpose, and so this alpha transpose becomes K transpose upon N, and so I can say here that N transpose becomes here R alpha transpose, which is now here equal to R K transpose upon N. So, that is the very simple result and it is based on the result from the linear estimation and vectors and matrix theory. So, anyway, now we have proved this result, and now we try to see that what is really happening with this one. So, now the result says that our connected block design is said to be orthogonal if and only if the incidence matrix of the design satisfies the condition that this one R K transpose upon N. And obviously, the designs which do not satisfy this condition, they are called as non-orthogonal. So, now if you try to see at the structure of R K transpose upon N from here, you can also do a small analysis that you can see here if there is any entry in this incidence matrix N which is 0, then the design cannot be orthogonal because you cannot express N transpose in this format, that is R K transpose upon N, right. So, now we have a very simple rule that if at least one entry in the incidence matrix N is 0, then the design cannot be orthogonal, right. And that is why if you try to see, when we considered the concept of incomplete block design, then initially we had taken the definition of Nij, and we had said that Nij can take value 0, can take value 1, or can take any value. This is simply trying to indicate the total number of treatments in the ith block. That means, so how many times the jth treatment occurs in the ith block. And then in the case of incomplete block design, you have a flexibility that a treatment may appear in a block or it may not appear in a block. So, now Nij equal to 0 is going to indicate that a particular treatment is not appearing in a block. And so, one can say a block design with at least one 0 entry in the incidence matrix is called an incomplete block design. Right. So, you can see here how the things are interrelated with each other, how these concepts are going to give you a very general structure. Now, we have here a sufficient condition. Remember one thing, this condition what you have used here, N transpose is equal to RK transpose upon N. This is a necessary and sufficient condition, and we have only here a sufficient condition for the orthogonality of the design is that Nij upon Rj is constant for all j. But remember one thing I will say, this is only a sufficient condition, right. So, now in case if you now try to see the connection between the orthogonality of a design and the connectedness and try to connect it with the definition of incomplete block design, then we can say here that the condition of orthogonality of a design, that a design which is not connected and an incomplete block design, even though it may be connected, cannot have an orthogonal structure, right. So, I hope now the things are getting clear to you. But now if you really want to understand, my very sincere advice to you all is that you try to understand all the concepts whatever I have explained you, and then try to interconnect two concepts at a time and then try to compare it with your randomized block design. And then try to see that whatever concepts you are trying to use here, are they getting satisfied in the case of randomized block design. And once you try to see it, then possibly you can interconnect it with the incomplete block design, that why this change is happening in the case of incomplete block design in comparison to the randomized block design. So, now we are talking of randomized block design again and again. So, why not to obtain the structure of randomized block design using the structure of incomplete block design? And you will see here that whatever you have obtained, in case if all the conditions like as orthogonality, connectedness, rank of C, etc., they are satisfied, you get here the structure of randomized block design. And you will see here that just by using the particular values of say Nij's, the incidence matrix, block total, treatment total, etc., you can obtain the structure of randomized block design with the structure of incomplete block design, right. So, if you try to recall, the randomized block design is an arrangement of V treatments in V blocks of V plots each such that every treatment occurs in every block, one treatment in each plot. So, and the arrangement of different treatments within a block, that is random. And now, if you try to translate this condition in terms of the terminology that you have learned in the case of incomplete block design, then I can say here that every treatment is appearing in every block once and only once. So, I can write down here Nij is equal to 1 for all I goes from 1 to B and j goes from here 1 to V, because there are B blocks and V treatments. Now, in case if you try to obtain here the value of here Ki, which was equal to summation over j Nij, this will come out to be here V, because you are trying to say that the total number of plots in a block have to be the same as the total number of treatments, so that every treatment appears in every block once and only once. And you are trying to say that here Rj, which is defined now here as say summation over j Nij, this will come out to here B, because every treatment is being replicated in every block once and only once. So, what will happen that you have here total B blocks. So, every treatment is appearing in each of the blocks. So, this Rj will become B for all j. Now, if you try to see here the sufficient condition what you have just observed, that Nij upon Rj. What is this? This is simply here 1 upon B, which is constant for all j. You can also check here the condition that N transpose is equal to Rk transpose upon N, and you can find out that this is an orthogonal design, right. And now, if you try to recall, means I would say try to look back into the definition of Cjj, Cjj prime and Qj that we had obtained in the beginning of the incomplete block design analysis, and try to substitute all the values which you have just obtained there. And then you can obtain here Cjj is equal to like this, b minus b upon v, and Cjj prime will obtain be here minus b upon v, and Qj will be obtained here as a Vj minus g upon v. And then if you try to recall, at that time you had written the normal equation for tau j as a Cjj tau j plus Cjj prime tau j prime is equal to, say here, Qj. So, if you try to substitute all these values here, you will get here this normal equation. And now you are trying to say here that tau 1 plus tau 2 plus tau v is equal to here 0, right. So, now you can see here, once you try to put this condition, that means the rank becomes deficient by 1. For example, if you have, suppose here tau 1, tau 2 and tau 3. Suppose if I say that tau 1 plus tau 2 plus tau 3 is equal to 0, then if I tell you that tau 1 is equal to something, tau 2 is equal to something, then tau 3 is going to be dependent on the values of tau 1 and tau 2, right. And then if you try to simplify here this equation here, you get here b into tau j minus b upon v into summation over j tau j is equal to Vj minus g upon v. And if you try to simplify here the value of here tau j from say here, right, you get here, because you see summation tau j will become here 0. So, you can get here tau j hat like as 1 upon b Vj minus g upon v. And if you try to recall, this is simply your here y bar naught j minus y bar double naught. After a long time we are using this expression, but this comes out to be the same what we had obtained through the principle of least squares there. So, you can see here now this tau j hat is the same thing what we had obtained earlier. And now if you try to obtain the sum of square due to treatment, which is now adjusted, so for the blocks, then it was obtained as summation tau j hat Qj. And if you simply try to substitute here the value of tau j hat and Qj, you get here this expression. And if you try to open it, this comes out to be summation over j Vj square upon b minus g square upon bv, which is the same as the sum of square due to treatment that you obtained earlier. And in this case, you are trying to obtain this as adjusted sum of squares due to treatment, and this adjustment is coming because of the block effects, and this is coming out to be the same as if you have obtained the unadjusted treatment sum of squares. Why? Because this design is orthogonal, right. And the sum of square due to blocks, that if you try to recall the way we had obtained in the case of analysis of variance, in case of designs, in the case of incomplete block design, it was something like this, is the same quantity summation bi square upon v minus g square upon bv, and sum of squares due to error was obtained here, SSE was obtained simply by quantity. And here if you try to see here the incidence matrix n, that will be your here B cross V matrix, where all the elements are going to be here 1. So, now you can see here all this expression what you have obtained here, they are the same as you have obtained in the case of analysis of variance under the setup of a randomized block design. Right. So, now we come to an end to this lecture, and you can see here that in this lecture we have completed the so called intra-block analysis of variance. We have now developed all the properties, orthogonality, connectedness, etc. And if you try to join them together, you can have a complete idea what is happening in the case of incomplete block design. And then towards the end, we also have obtained the randomized block design as a particular case of the notations and symbols used in the case of incomplete block design. So, now you can ask me that then why I had spent so much of time in giving you different types of block designs in the beginning. Why not I can come directly to the incomplete block design and can explain you. Now, instead of answering this question, if you try to recall that if I simply try to give you the incomplete block design directly from the first lecture, I jump directly to the matrix notations. Can you really understand it? Possibly it is very difficult, because for so many years you have been handling this these terms through the summation approach. Now, after this lecture, you are well versed with the concepts in the case of intra-block analysis of variance, and now you can obtain all the things directly. So, that was the reason that why I had to spend that much of time in giving you the basic fundamentals, so that you get confidence that you can do it, and then now I have given you the basic results that is related to incomplete block design. So, incomplete block design can become a complete block design under certain conditions, and those conditions we have now studied and we have now understood them. So, now I request you that you try to have a look at this incomplete block design right from the first lecture, and then try to see how the things have been interconnected by giving different types of concepts, definition, and then it will give you a lots of enjoyment once you understand it. So, you try to enjoy the course, try to revise it, and I will see you in the next lecture with inter-block analysis of variance of incomplete block design. Till then, goodbye.